to the channel. So we are continuing the series of solving interview experiences from Lead Code. Every day I pick one interview experience and try to solve all the DSA questions there. Not only that, we also try to solve all the possible variations of that question that can be asked during the interview. I have already reviewed some of the interview experiences previously, so please check them out. In today's video, we will be solving the data structures and algorithms question of this D.E.Shaw interview experience, which was posted around 6 hours ago. So let's move to the DSA interview. Uh, let's solve the first question, wherein given an array, consider all the subarrays and return subarray with k largest sum. So let's try this. So we have given this question, like given an array, consider all the subarrays and return the subarray with kth largest sum. So the problem is simple. Now, before moving on to the solution, uh, I would again encourage you to pause the video and try to think of any ambiguity that you can think of in this statement. So if let's say interview asks us this statement, then is there any ambiguity in this statement or not, whether we should clarify it or not. So let's discuss some of the follow-ups that we can ask to clarify the question. The first one is can condition of like can addition of all the integers can overflow the 32-bit integer. So basically we have to consider a subarray and find their sum. So it may happen that individual numbers are less like fit in the integer, but their sum may not fit in the integer. So this can be a good question to clarify. Basically, if all the sum of all the subarrays fit in 32-bit integer or not. So for the purpose of this question, let's assume the answer is no. Like the sum might not be able to fit in 32-bit integer and might overflow 32-bit integer. So moving ahead, the second ambiguity that we have in this question is what does kth largest signifies? So basically, the question states that we need to find the kth largest, right? But it didn't specify from where, kth largest from starting or from ending. So basically, if let's say if our arrays look something like this, 1, 2, 3, 4, 5, 6, 7, 9, 10. So kth largest, let's say we have to find the third largest. So third largest can be this or it can be this, depending on where we are starting from. So it is a good question to ask, basically to clarify whether what does kth largest signifies. So for the purpose of this question, let's assume that it signifies this. So if we want to find the kth largest in this array, this will be our kth largest. So we are starting from the smallest one and then finding the kth largest. So that's like one of the question that we can ask. There is some other ambiguity. Let's discuss that as well. So one more ambiguity can be, does the array contains negative integer? So like we have an array, it didn't specify whether it can contain negative integers or positive integers. So our solution will differ a lot if it contains negative integer. We will look at in a moment how solution will differ if the array contains negative integers. So for the purpose of this question, let's assume that the array doesn't contains negative integers. Uh, we will also look at the case where array contains positive integers. So stay tuned till the very end. Now, now we have clarified these questions. So basically, we have clarified these three questions and we have got these three answers. So basically, the sum of the subarray can overflow 32-bit integers. Uh, kth largest signifies starting from the smallest, we have to find the kth one, and our array will not contain any negative integers. So now our question is clear. Let's try to understand this with an example a little bit better. So uh, let's say this is the array, initial array 1, 2, 3, 4. Okay, and we have to consider all the subarrays. So what are the subarrays? One subarray could be like this, just one. One subarray could be 1 to 2. Another subarray could be 1 to 3. Another one is 1 2 3 4. Similarly, uh, another subarray could be 2, then 2 3, then 2 3 4, and uh, then 3 can be one subarray, 3 4 can be another subarray, and then fourth one, like only 4 is just one subarray. So we have calculated the sum of each of these subarrays. So 0 0 means this subarray, so the sum is 1. Similarly, 0 3 denotes this entire subarray, and the sum is 10. Similarly, for 2 3, the sum is 7. Like 2 3 means this subarray, so the sum is 7. So now we have sum of all this subarray. So now we will, like if you remember, we have to find the kth largest. So let's just sort this entire thing. So after sorting uh, this range of elements, we will get this. Now in here, if we have to find the third largest will be this. If you have to find the fifth largest will be this. So that's what the question is. Now one simple solution could be just to find all the subarrays, sort it, and then return the kth largest. So like what is the time complexity of this approach? First we are calculating all the subarrays. So number of subarrays could be order n square. Then we are sorting all this subarray. So sorting all the subarrays will require uh, n log n time. So here total number of elements in the subarray is n square. So total uh, time that will be required to sort the array will be this. So basically, if we just write in remove the constant factors and all, we will end up in n square log n. So that will be the final time complexity if we just sort the array without doing any kind of fancy operations. So that is one solution, but clearly that is very slow. We can do much better. And given that the array doesn't contain negative numbers, we can do much better. We will look at how. So remember, like the current complexity that we have looked at is n square log n. Okay, so we will see how much better we can do from this complexity. So now the idea is, like if we are not calculating the sum of all the subarrays, so basically we will not, like we have to do better than this, right? So we have to just let's say do better than n square. So if we have to do better than n square, no matter what, we can't calculate all the sum of all the subarrays, right? So we have to find a way wherein we are not calculating the sum of all these subarrays, but we have, like if required, we can calculate the sum of subarrays easily. So this point us to like very standard method called prefix sum. Okay, so if we have prefix sums, then we can calculate the sum of any subarray within constant time. So that's the first point. But what we will do with the prefix sum? Like we can calculate prefix sum, but we have to find the kth largest, right? And for that we need either this entire set, uh, otherwise we can't do much with prefix sums as well. So now comes the interesting fact. Like if we can't enumerate all these n square subarrays, uh, what we can do, let's do the other way around. Basically, instead of enumerating it, let's try to answer whether uh, x, like what if we have x, then how many numbers are there which are less than x? Like if we have x, if we consider x as our as one of the number, then how many numbers in this set, basically the entire subarray set, is less than equals to x? So what we are trying to do, we are trying to find whether 1 is an answer or not, whether 2 is our answer or not, whether 3 is our answer or not, 4 is our answer or not, and so on and so forth. So basically, we will take each candidate. Let's say we take 8. So what we will try to answer is whether 8 can be our answer or not. So how 8 can be the answer? If 8 is the kth largest number. So basically, we have to answer uh, how many numbers are there, how many numbers are there which are smaller than 8, right? So if we answer this, let's say if we find an efficient way to answer this, so we know an efficient way to answer this question, like how many numbers are there which are smaller than it. Then if this, let's say this, the answer for this is something like maybe t. So if t is less than, if t is equals to k, then we basically say that 8 is our answer, right? So that's the approach basically we are trying to follow. So we we are trying to just go one by one, from starting from very minimum, which is 1, to uh, next greater elements. For each element we are trying to verify uh, what is the, like how many numbers are there which are smaller than it, and if the answer comes to be k, then we will say that this is the required answer. So having said that, now let's say somehow we magically know how to do this efficiently. Now even iterating over this is very tricky, right? Because we have lots of numbers. Like let's say the total sum here is 10, like the largest sum in this question is 10. So we have to go from 1 all the way to the largest sum, which in our case is 10 in this example. So this is also not efficient, because total sum of the array can be way larger than n square itself. So they like array may contain 10 to the power 9. So it may be possible that n square is itself is greater than 10 to the power 9. So basically we can't just iterate over this one by one. So we need to find a way where we are not iterating over each and every possible combinations. So what this points to, basically we are doing linear search. We want to do something faster than linear search. First approach that comes to your mind is binary search. So what happens in binary search? Basically you have a set of numbers, you try to partition it in the middle, and then either you will say that you will be searching in the left, or you will say that you will be searching in the right. Both, like either in the left or the right. Either way you are like uh, escaping half of the array. So that's what binary search is. Now how binary search is applicable to this scenario? So let's say we split our array here. Now basically 4 is the split point. Now let's say the number of largest, like let's say the number of elements smaller than 4 is let's say number of elements smaller than 4 is 5 in our in this set. Number of elements smaller than 4 is 5. So and we have to find the let's say k is 3 here, and we have to find the third largest element. So basically before 4 there are 5 elements, right? And we have to find the third largest. So does it make sense to search in the right half of the array? Because if for if before 4 itself there are 5 elements which are lesser than 4, then after 4 there will be more number of elements which are lesser than this 4, right? So it doesn't make sense to search in the right part of the array. So we will just search in the left part of the array. So basically if k is less than the answer of this question, uh, uh, or basically k is greater than the, so the answer of the question is, let's say, is t. So if t is less than k, or basically t is greater than k, then we will search in the right part of the array, because number of elements smaller than 4 is itself larger than k. So it doesn't make sense to search in the right part of the array, because in right there are larger elements than 4. Similarly, if it is less than or equals to, we can search in the left part of the array. So clearly we can apply binary search here. So now only question that remains is how to calculate this function efficiently. So we can do binary search here. So the binary search will require log of the total sum of the array time. Now this will be multiplied by what we come up for this, like how many numbers are there which are smaller than it. So let's try to solve this particular question itself. So we have to solve this particular question. How many numbers are there which are smaller than 8? So let's take an example. So let's say our initial array is 1 2 3 4, and we have to find uh, how many numbers are there which is smaller than 8 in all the subarrays of this array. So how to find this? First of all, like we can't iterate over each and every subarray, otherwise we will end up with again n square in our time complexity. So we can't do that. So let's start from the very beginning. So let's say we are uh, we are considering this subarray one. So whether one is smaller than 8 or not, it is right. So we will add one to the answer. Now let's consider this 2. So there are two subarrays possible with 2. One 2 itself, second is 1 and 2 both. So like ending at 2, how many? So one thing to note here is, if you remember, we have the answer of this question, like does subarray contains negative numbers? This answer is no. So if this answer is no, if we calculate just prefix sum, let's say we calculate the prefix sum would be something like this. So if we calculate the prefix sum will be strictly increasing, right? So if we want to answer that how many subarrays are there ending at 2 which are smaller than 8, then how will we answer? So every subarray ending at 2 can be like sum of every subarray ending with 2 can be denoted by p of 2 minus p of I, right? So every subarray ending at 2 will have this sum, because we like, p is the prefix sum. So every subarray ending at 2 will have this sum. What we want is how many subarrays are there such that this sum is less than equals to 8, right? So basically what we want is, let's just do a little bit of so what we want is p2 minus 8 is less than equals to pi, right? So what we want is how many PIs are there such that they are greater than or equals to P2 minus 8. So that's what the question now becomes. So this can be done very easily, right? With binaries, like with a simple set or a hash map or something like that. So basically what we want to find is how many numbers are there which are smaller than a particular number. So this can be done very easily, right? Basically what we have to find here, let's say we have this prefix sum 1 3 6 and 10. So what we are trying to find is how many subarrays are there ending at this index 2, uh, which is smaller than, like whose sum is smaller than 8. So basically we are trying to find how many indexes in this p subarray is there such that it is greater than equals to 3 minus 8, which is minus 5. So there are total two indices here, one like this one and this one. So that's where we will add 2 in our answer, because we have two indices in this array which is smaller than 8. Similarly, for subarray which is ending at 6, we will do the same thing. Number of integers such that number of integers such that the sum is like the value is less than 6 minus 8, which is minus 2. So again, we will have like this three integers, 1, 3, and 5, 1, 3, and 6. So we'll add 3 to the answer. Now again, for 10, we will do the same thing. Number of integers such that the sum is greater than 10 minus 8, which is true. So in this case, we will get these three integers, 3, 6, and 10. So we will just add 3 to the answer. So total we get 9. So there are total 9 subarrays whose sum is less than equals to 8. So just to reiterate, what we have done is we have calculated the prefix sum. Now, once we have calculated the prefix sum, we are saying that the sum of any subarray would be something like p of I minus uh, p of j. So sum of every subarray ending like starting from I and starting from j and ending at I will be p of I minus p of j. So now if we fixed this p of j, basically what we are saying is how many subarrays are there which are ending at so let's fix this p of I. So how many subarrays are there which are ending at I? Let's say the ending at 3, such that their sum is greater than or less than equals to 8. So what we have done is we have fixed this I, and now we are asking the same question: how many subarrays are there such that their sum is less than equals to 8? And by just arranging this a little bit, we will get like how many. We have to just find how many integers are there such that their value is less than this. So this we can find very easily uh, because the array is sorted. So because the array is sorted, it means we can do binary search and then just find what how many integers are there which are smaller than this. So hope the approach is clear. Let's just look at the pseudocode for this solution. So the pseudocode looks something like this. So so just a second. So the pseudocode looks something like this. So basically, find calculate the prefix sum of the array. Okay. Once you have the prefix sum for each index I, like we are fixing in index I, if you remember that equation, for each index I, we want to find uh, index j up to which this condition is true, right? And what this finding this index j is just another binary search of the array because the array is sorted. So if you remember, the array contains only positive integers. So if we take the prefix sums of the array, it will come something like this. It will be increasing. Now because it is increasing, we need to find an integer uh, which satisfy this equation. So basically, again taking this to the right side and taking this to the left side, we will just get like all the integers uh, whose sum is greater than or equals to pi minus sum. And basically this we can find this is constant value, and we have to just find this j index, which can be easily find in this using binary search. So for let's say if you have to find all the like indices which have value less than equals to let's say 7, then we can say we'll do binary search and 7 comes here. So that's where we'll say that there are two integers, sorry, so 7 comes here. So there are one integers which is greater than or equal to 7. So we will just add 1 to our answer. Similarly, for this, we will say that okay, 6. How many integers are? Let's say if this entire thing comes to 6, and we have to find how many integers which are which are greater than equals to 6. We will end up here, and we will say that these two are the integers which is greater than or equal to 6. So just add 2 to the answer. So that's the approach. Basically, we are just iterating over, we are just fixing one index I, and we are finding the index j up to which this condition is true, and then adding this I minus j to the answer. So what's the overall solution? Like this is the function. If you remember, we have initially did a binary search over the answer. Like what would be the answer of the original question, and in that we need this function, and this is the implementation of this function. So let's just reiterate over the entire solution once. So what we have to find is uh, we are given an array 1, 2, 3, 4, let's say, and we have to find the fourth largest element of this array. Okay, so what we have done is we have tried all the possible values of the answer 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and so on. So we will try all the possible value of answer, and we will call this function. So basically this will denote the number of elements which are less than or equals to this particular value, let's say 4 or 5. And if it is equals to this k, like k is our 4, so if it is equals to k, then we will just return the answer. So now in because we can't iterate over every of these possibilities, we are doing binary search over it. We are just dividing into half, and then either searching over the left or the right, and how to like whether to go left or right depends on the value that will be returned from this function. So let's say the value returned is t. So if t is greater than k, then we will go to the left, otherwise we will go to the right. So hope the entire solution is clear. Let's just look at the code once. So this is the get kth largest uh, like the function, and we are taking in an array and the kth number for which we want to find the answer. And if you remember, the sum of the array can overflow the integer, so that's where uh, the answer can also overflow the integer. So we have to take long, so it return type will also be long. Now we are doing binary search over the answer. We are finding how many numbers are there which are smaller than or equals to this m. If this is less than k, we are just moving to the right of the array. If it is greater than or equals to k, we are moving to the left of the array. Now, as discussed, this function count of smaller or equal subarray, basically we are first calculating the prefix sums. Once we have prefix sums, for each indexes, we are finding the index up to which this condition will be true. Like how many indexes are there such that pi is greater than or equals to pj minus sum, right? That's for the equation. So this is what uh, like we have to find all the indexes whose value is greater than this. So we are just iterating like doing a binary search over this prefix array for this scan, and just returning this like just giving, so basically uh, returning this value. Now in the result we will just add j minus index and return the result finally from this function. So I have tested this function already with simple array. So for second largest it should give 2. That's what it is giving. Let's test the sixth largest. So for sixth largest, 1 2 3 4 5 6, sixth largest is fifth. So if you call this, it will return 5. It will return 5. So that's what the solution is. So hope the solution is clear. If you have any doubts in this, please ask them in the comment section below. So now let's move forward with the second part of the question. So basically we have assumed that the array contains negative number, like array doesn't contain negative number. But what happen if array contains negative numbers? So what happen if the answer for this will be yes? So in that case we can't apply binary search for this function. So this, like we have to find this index j, right? So we can't apply binary search here. So if we can't apply binary search here, this part will take order and time, and as we are iterating over each indexes, this will again take order and time. So total, we will, like, this entire function will require order n square time. So the complexity will be again order n square into log of total sum. So that will be the complexity. So this complexity is again not a good, if we, like previously, like if let's say the in our previous solution, when the answer was no and we are doing binary search, this part was taking log n time. Okay, so this entire function was taking n log n time, and we are calling this function for, like, inside a binary search. So that brings sense, the another log of sum. So basically, that was the time complexity before, but now when they say that okay, there can be negative numbers, so this prefix sum will not be a strictly increasing array. So that's where we can't apply binary search, and hence uh, this we can't do binary search, and we have to do a linear search, and this log will become n. So then complexity will be n square into log of sum instead of n square n log n into log of sum. So, but in that case we can do better. Like like notice that we have n square in this complexity, right? So if we already have n square in this complexity, why not calculate all the subarrays? So let's enumerate all the subarrays, and then what we end up is, we are given a set of numbers and we have to find the kth largest number. So this is a standard problem which can be solved using heap. So we have given a set of numbers, we have to find the kth largest number. We will take the first k numbers, put it into heap, and then for every next number we will compare it with the smallest number. If it is smaller, then we will pop one number and push that number to the heap. Again, compare the next number. If it is smaller, do the same thing, and so on and so forth. So basically we are taking only k numbers at a time in our heap, and this will give us the k smallest number in this entire array. So then the complexity will be, to enumerate the array we will require order n square time, like to enumerate all the subarrays, and then we are for each element we are pushing back, like pushing it to the heap or popping it to the heap one time. So total complexity in that case would become order n square log k, so which is better than n square log of sum. Like not that much better, but still it is better than n square log of sum. So if array contains negative numbers, then like we can't solve it in this efficient manner. Instead, we have to solve it using heap, and the solution will be of complexity n square into log k. So I'm not implementing this solution. This is a very standard. This should be a very standard implementation. You should try that as an exercise. You can paste the link in the you can paste the link of your code in the description below. If you want me to review it, I will review it and let you know if that's correct or not. So hope you enjoyed it. If you have any doubts, please feel free to comment them below. I will answer them, uh, and we will be back in solving the next set of questions in an upcoming video. So thank you.